chance that movement of that particles will be high, but it will be more. That solution quantity will be more, means solute particle is same, but the quantity of a solvent is high. Then what will happen? The chances of this cation or anion and repulsive force factors, so that will be very less. So that is what you call the limiting molar conductivity. Limiting molar conductivity is just indicated to the that is a law, that is Paulus law, is that of limiting molar conductivity. In that position, that what will happen? So that limiting in the limiting molar conductivity, what will happen? These things is see that when the one cation and what is the that amount number of cations is formed, and anion what is the number of anions is the formed. So on the basis of that, it is the limiting molar conductivity. Okay, and this is the formula. This area is the formula. This particular area is the formula of that's what limiting molar conductivity is the number of cations plus concentration value, and number of anions, then concentration value. So on the basis of that, you can calculate of that particular things. Okay, now the thing is that it will come down here. See, that is limiting molar conductivity value. Okay, then now will come down the ionic, what I told you, that mobility. Okay, that mobility is depending upon the concentrations. See, simple things, very simple things. If the concentration will be high, so then the chances of the closeness of the similar charge particles, means maybe cation or maybe anion, similar charge particle, chances of repulsion, that is chances of closeness of the charge, but similar charge particle, then the Tyndall effect or Brownian movement or electrophoresis, whatever that movement, zigzag movement will be arises. So on the basis of that, if we calculate, then what will happen? So if the concentration will be more, then what will happen? The chances of the closeness of the similar charge particle is high. Then what will happen? Then zigzag motion or this electrophoresis Tyndall effect, what do you say that meaning of that one? So that will be arises. If the chances of the concentration is less, then this movement is very less. Then what will the mobility will be less? What is the meaning of mobility? See, if I'll come close to the similar charges, it will put two magnet of same pole in the arrange the two magnet in the on the basis of the same pole, means north pole, then repulsion will be high, right? If the distance will be high, then repulsion will be less. If we make the two same kind of magnet, same that is pole magnet, come close, distance will be less, then repulsion will be high. If we make them more distance, repulsion will be less. Simple thing. That physical your what is that magnetic theory you can put in that in this chemical that is chemistry of that particular ionic mobility. If ionic mobility will be high, if that similar charge will come close, means concentration will be high. If the ionic mobility will be less, if the concentration is less and the distance, means that concentration is less. This is the similar factor of that one. Okay, now I'll come down. That dielectric limiting molar conductivity is there. What I told you exactly, that is on the basis of Paulus law of electrolysis. So that is the limiting that this is the formula area of that one. On the basis of that, you have to do the numericals. Okay, so it will come down that ionic mobility is the effect. Now the fact is the effect. See, that is effect of other factors on the conductivity. That is, it is important one. Okay, so effect, how the effect are responsible for the conductivity. Okay, if the temperature will be there, if the temperature, okay, if I raise the temperature, so what will happen? If the raise the temperature, then ionic mobility will be high. You know that when you provide the external temperature, that energy associated with that charge particles, then what will happen? Then the kinetic energy increases. Kinetic energy will be high, right? So that is the important. But the thing is that, so this is sometimes depending upon the concentration as well as depending upon that what is that concentration. Okay, depending upon the concentration. If the concentration is high, then mobility will be high. Okay, if concentration is low, the mobility will be low. Again, that is the fact, because everything depending upon the concentration. Okay, if pressure has no effect. Okay, pressure has no effect on the mobility of that one. So that is why the conductivity of all electrons increases with increase in temperature. I told you, but thing is that it is depending upon the concentration. As you provide the external force, external energy to that particular molecules, then what will the kinetic energy obviously increases. So if the kinetic energy will be increases, then what will the mobility of that particular species, what species is associated in that solution will be increases definitely. But important thing is that concentration. If the concentration is high, definitely the mobility will be more, because again that striking force, collision will be there, similar charges will collide each other, then that is what is a zigzag force will act on that particular species. Then what will happen, they will move in the randomly in zigzag ways, right? What will happen that if the variation of the molar conductivity at the infinite solution, okay, infinite solution, okay, that is the one more thing, the conductivity increases slightly with increase in pressure. So actually slightly, see that is slightly pressure, if you see that if you increase the pressure, what will happen, the concentration will be increases, no problem. But thing is that that gap between the two molecules will decreases, then mobility will be decreases, slightly increases. There is no meaning of slightly increases, I don't think so. Slightly increases has some effect, so that's why straightly we just don't think that. But in the practical we will see it is mild increases of that particular mobility. But what will happen, why? Because if you put the pressure, see that what will happen, the pressure as it is liquid junction, right? Liquid that is, if it gas, okay, it may have, but liquid is least compressible. Liquid cannot be compressed, right? Liquid cannot be compressed. As you are discussing about the solution, that is your liquid solid solution or liquid solution, then what will happen, the pressure has no effect. So as the pressure has no effect, then it will have that is there is no impact. But if it gas, so definitely there has effect, right? If it will come down to the gas, then what will happen, the pressure gas is highly compressible, then it has some effects. Okay, next, it will come down, sorry, just a second. Okay, now effect of a solvent, obviously solvent has solvent has more effect on that mobility. See that why solvent is more effect. See that in solvent are different types. Absolutely, solvent is different types. It is a highly polar solvent, means if it is water, it is that is polarity, and there if you taking the acid, that is again polarity. It is dipolar, or that is a dielectric, or means your what type of a solvent you are taking, that is most important. Okay, so on the basis of solvent, this scenario will be changed. So the dielectric constant having a small ionized effect on the electrolytes, small ionized effects. Okay, so the electrostatic force between the oppositely charged ions would be appreciably equivalent conductance will have the value. So however, solvent with high dielectric constant have more conductive solution. So see what I told you, different type of solvent having different type of effect. If it is high dielectric, so effect will be high. It is low dielectric, means dipole moment. Dielectric means dipole moment. Moment of the that is shared pad bond will move towards the highly electro. If we take the example of that is HCl, okay. So hydrogen has the that is dipole, hydrogen has the that is dipole moment is 2.6, and chlorine is around 3.5, 3.4, 3.5. So chlorine is high electronegativity value, has the high electronegativity, hence the what will happen, the electron of hydrogen move towards the chlorine, so it is polarity. So in this sense, if dielectric, that means more highly polarity substance you are taking in that particular as a solvent, so definitely what will happen, that effect will be more. But if we take the lower, that is if we take the example of that is what is that acetic acid, okay, it is low dielectric in nature, so that's why what will happen, so this kind of a solvent has the low electroconductivity nature. Okay, then viscosity medium, absolutely viscosity medium is the most important factor here, that the dependence of a conductance on the viscosity of the medium is given by Walden rules, according to which the equivalent conductance of electrolyte is inversely proportional to the viscosity. See, that is I told you that this has the much more value. So because viscosity depends, you know that viscosity. So if viscosity is in, if high viscous, then surface area will be low activated, then what will happen, that the movement of the particles will be less. So that's why you are telling high viscosity, less movement. So that means it is inversely proportional. You have to understand these things. So if viscosity, people say that you will take oil as well as water. If the solvent is oil and water, so obviously oil is more viscous than the water. Hence that is your what is the conductivity in that oil is less compared to the water. So that's a water is a good medium of a solvent. Okay, next we'll come down to that area. So this is the question and all the things. Okay. Okay, now I will come down the measurement of electrostatic conductance. We have discussed about the Houston principle already. We have discussed that one. I told you how it acts and how that is calculated in that case. Okay. Next. Okay, by using the this is okay. Now we'll come to the conductometer. Okay, so let's go to one that is video. I'm sharing one video with you. Go through this.
The principle of conductometric titration is based on a solution's electrical conductivity, which is in turn attributed to the ions that's present in the solution. It's important to understand that conductivity is proportional to the amount of ions present. The more ions there are in a solution, there will be more charge carriers to carry the electrons from one side of the solution to the other side, which then gives us a greater conductivity. This is particularly relevant in the context of acid and base solutions because acid solutions will produce hydrogen ions in water and conjugate bases, which sometimes can be ionic as well. For example, hydrochloric acid will dissolve in water to produce either hydrogen ions or hydronium ions, as well as chloride ions. Both ions will contribute to the conductivity of the acid solution. Similarly, base solutions can also be conductive because they can produce hydroxyl ions and conjugate acids, which can sometimes be ionic as well. For example, ammonium ionizes water to produce ammonium ion and hydroxyl ions. Therefore, when you think about an acid-base solution and its conductivity, there are really two main factors that will determine how conductive the solution will be. The first factor is concentration. Greater the concentration of an acid or base solution means that there will be more moles of ions present in that solution, and that gives you a greater conductivity. The second factor is strength. Strength of an acid base is related to the degree of ionization. When we say that acid and bases are stronger or have greater strength, we mean that they have greater degree of ionization. So a greater proportion of the acid and base molecules will produce ions. And of course, that will lead to more moles of the ions present per volume, and thus a greater conductivity again. Although all ions will contribute to the conductivity of a solution, some ions are better conductors than others. It's important to remember that hydrogen ions from acids and hydroxyl ions from bases are the most conductive ions in solution because they're the most mobile. They move around solution the most easily due to their smaller sizes compared to other ions. Now, you don't need to know these numbers for conductivity, but hopefully this gives you a better idea for comparing the relative conductivity between the ions that you will usually come across in acid-base chemistry. The setup for conductometric titration is quite similar to that of normal titration using indicators. We again have two components. We have the burette, which contains the titrants, and this can either be the acid or base. Usually, instead of a conical flask, we have a beaker instead, which contains the other chemical. That's either the unknown solution that we're trying to analyze, or this can be the standard solution. We use a beaker because we can then insert electrodes into the solution and connect these electrodes to an external circuit with an ammeter so then we can measure the currents that can pass through the solution.
So that main that objective to share this video is that how actually how I'll do this one, how that is what type of procedure is this, how the electroconduct means conductometric titration will be conducted, and where you have to fit, and what is that, how to read the things. Okay, so that is the most important things.
The magnitude of currents is proportional to the conductivity of the solution. So when a solution becomes more conductive, the current size detected will then increase, vice versa if the conductivity decreases. So the principle of conductometric titration is based on the relationship between a solution's conductance and its ion concentration. A solution with higher conductivity will then yield a higher current reading on the conductivity meter. During the titration, as the titrant is being added from the burettes, we'll expect the ion concentration in the beaker to change, and this will then result in a conductivity change. Let's first go through a conductometric titration between a strong acid and a strong base. Suppose the burette contains a strong acid, hydrochloric acid, and the beaker contains sodium hydroxide. In the beginning, the solution of sodium hydroxide is very conductive because sodium hydroxide is a strong base, so it completely dissociates to produce a large amount of hydroxide ions and sodium ions. As hydrochloric acid is added from the burettes during titration, the concentration of hydroxide ions is decreasing due to the neutralization to form water. On the graph, as titration is being carried out, the conductivity of the solution in the beaker will then decrease. Now, even though the addition of hydrochloric acid also adds chloride ions to the solution, the addition of Cl- ions is outweighed by the loss of hydroxide ions, because recall that hydroxide ions are more conductive than other ions, such as chloride ions. So even though we are getting more chloride ions in solution, the overall conductivity of solution still decreases due to the loss of hydroxide ions. When the right amount of hydrochloric acid is being added to the sodium hydroxide to reach the equivalence point, the conductivity of the solution will reach its minimum value, because at this point, we have the lowest concentration of ions present, including sodium ions and chloride ions. After the equivalence point, further addition of acid will increase concentration of hydrogen ions, because these ions are no longer neutralized by hydroxide. And of course, this will result in an increase in conductivity as seen on the graph. In conductometric titration, we often see a turning point in the changes in conductivity as the titration is being carried out. In a strong acid and strong base titration, this turning point is very clearly identified as the minimum point of the conductivity curve. If we can identify the volume of acid being identified at the equivalence point, we can then work out the concentration of the unknown solution. The conductivity graph for weak acid and strong base titration looks a bit different. Suppose we have a titration between acetic acid, which is in the beaker, and sodium hydroxide, which is being added from the burettes. This produces sodium acetate and water. In the beginning, the conductivity of solution is relatively low because a weak acid only undergoes partial ionization, which in turn produces a relatively low amount of hydrogen ions and conjugate base acetate ions. The addition of sodium hydroxide from the
So thing is that here that weak acid, as we discussed in the last class, weak acid has means is very less soluble, right, in the water. If we take the example of water, less soluble in water, but that is weak electrolyte. You can say that weak electrolyte. Weak acid is a type of weak electrolyte. I told you that acetic acid, vinegar, and you are eating it is acid. Okay, we are using the acetic acid, but it is vinegar, and you know all the fast foods and all the things you are using this vinegar, right? You are eating also. It's around that is 6.7 is the that is pH of that one. So weak acid is a weak electrolyte, right? You have to understand this. You know what is that is, it is given that weak acid with a strong base. The titration is weak acid with, against the strong base. How the things will be conducted. So that is the thing.
burettes causes the small amount of hydrogen ions to decrease in concentration as it is being neutralized by the hydroxide. This results in a small decrease in conductivity as shown on the graph. Here, although the sodium ion concentration is increasing, we have a drop in the hydrogen ion concentration. Remember that hydrogen ions are much more conductive than sodium ions. This is why the conductivity still decreases. In the second part of the graph, when the small amount of hydrogen ions are being neutralized, there is a shift in equilibrium position in the ionization reaction of acetic acid with water. Due to Lachauss's principle, this is to produce more hydrogen ions and acetate ions. This equilibrium shift will then produce more hydrogen ions, which are quickly neutralized by the further addition of hydroxide, more acetate ions, and of course, as sodium hydroxide is being added, we also get an increase in sodium ions. The additional increase in acetate ion concentration causes the conductivity of the solution to increase slightly, as you can see in the second part of this graph. Once all the hydrogen ions that could be deprotoned from the weak acid have been neutralized by all the hydroxide that can be added, we have reached the equivalence point of the titration. After the equivalence point, any further addition of sodium hydroxide will then increase the hydroxide concentration as well as the sodium concentration. This will result in an increase in conductivity at a much faster rate compared to before, because hydroxide ions, being the more conductive ion, is now increasing in concentration as well. So the equivalence point of a weak acid and strong base titration can be identified by looking for this change in the rate of increase in conductivity in the titration graph. A similar conductivity graph will be observed for a titration that has a weak base in the beaker and a strong acid being added from the burette. In a conductometric titration where a strong acid is in the beaker and a weak base is being added from the burette, the conductivity starts off relatively high due to the fact that a strong acid completely dissociates. As the weak base, such as ammonia, is being added from the burette to neutralize hydrochloric acid, the concentration of hydrogen ions that was in the beaker decreases due to neutralization. Although the ammonium ion concentration is increasing, the conductivity of the solution still decreases because hydrogen ions are much more conductive compared to ammonium ions. When the titration reaches the equivalence point, that is when all the hydrogen ions have been neutralized, the conductivity reaches its minimum value. So this is the equivalence point of a titration between a strong acid and a weak base. At this point, we only have ammonium ions as well as chloride ions. After the equivalence point, the addition of ammonia only increases the conductivity slightly. This is because ammonia is a weak base that undergoes only partial ionization. So it produces a small amount of hydroxide ions and a small amount of ammonium ions. Despite the slight small increase in conductivity, we can still clearly identify the equivalence point of this titration by looking for the bottom part of this V-shaped curve. The titration between a strong base in the beaker and a weak acid from the burette will also look like this. As an extension example, the conductometric titration between a weak acid and weak base looks vastly different. Again, the conductivity starts off relatively low due to the partial ionization of the weak acid. As the base is being added, the small amount of hydrogen ions that was present are neutralized, which results in a small decrease in conductivity. When the hydrogen ion concentration decreases, by Lachauss's principle, the equilibrium position will shift towards the product side in order to counteract that change. And this will then produce more hydrogen ions and more acetate ions. The hydrogen ions are, however, quickly neutralized by the ammonia that's being added from the burettes, so we will only see an increase in acetate concentration. And of course, as we add more ammonia, we also get more ammonium ions. The increase in concentration of these ions will then result in an increase in conductivity, as shown here. When all protons from the weak acid have been neutralized by the addition of ammonia, adding more ammonia will result in an increase in hydroxide concentration because these ions are no longer neutralized by the presence of hydrogen ions. So now, after the equivalence point has occurred, the increase in hydroxide ion and ammonium ion will cause the solution to continue increase in conductivity. However, this will be at a different rate. Sometimes the rate will be smaller than before, sometimes the rate will be faster than before. Regardless of how fast the new rate of increase is, you can identify the equivalence point of this titration by looking at the turning point of the conductivity curve. 20 milliliters of potassium hydroxide solution was titrated with 0.2 mole per liter of sulfuric acid solution in a conductivity cell.
Now the thing is that you just understand how the strong base, strong acid, weak base, weak acid, then a strong base, weak acid, strong acid, weak base, how the titration has been done in the conductometric process, and how does it measure, right? So how the shifting of the four types of that titration. You have gone through this video experiment and all things. Okay. Now the thing is that this portion of that your syllabus is completed. This particular that chapter conductometry. Let's go to the another thing, another part of that one. That is your, just a second. Next unit is unit number 5. So that is electrogravimetry and colorimetry. Okay. So okay. So this is the chapter you right now. You are electrogravimetry and colorimetry. So these two are the quantitization titration. What do you say, the quantity? How to measure the quantity of that one, amount of quantity. So that is why this that electrometry and colorimetry is both the important area. So in this case, your objective has to that explain the principle of electrogravimetry, explain ohmic potential, that is iron drop, and how the polarization of the say their significance in the electrode position. Okay, calculate the potential of given cell in initiate deposition of the metal ion, and the calculate the residuals of concentration of the ions of the solution be measured commencement of the deposition of the next ion. So describe constant current and control potential electrogravimetry. All the things will be we have to go through. Okay. So now that electrogravimetric analysis, we have discussed this or that on, but let me to share one video with you. All of you go through this, you will understand better that one. Just a second, please.
Hey everybody, in this video we'll be talking about gravimetric analysis. Gravimetric analysis is a quantitative technique that measures the mass of a particular substance. There are two types of gravimetric analysis: precipitation and volatilization. In the precipitation method, the quantity of an ion is measured by measuring the mass of a precipitate that can be formed from the ion itself. In contrast, in the volatilization method, the mass of a mixture or compound is measured before and after heating. The intention here is to use the heat to remove a volatile substance that is present in the mixture or compound. We will discuss these two methods individually in this video. In the precipitation gravimetric analysis, a substance is added to the analyte of choice such that a precipitate is formed. For example, if we want to determine the concentration of sulfate ions in a solution, we can add a solution of barium nitrate to the solution containing the sulfate ions to produce a precipitate, that is, barium sulfate. This is shown in the picture on the right. It is important to keep in mind that barium nitrate must be added in excess to ensure that every sulfate ion reacts to form the precipitate of barium sulfate. Otherwise, when we measure the mass of the precipitate, we will underestimate the amount of sulfate ions present in the solution. Once the precipitate is formed, the mixture is filtered to isolate the precipitate. Then the mass of the precipitate is measured and used to calculate the quantity of the ion that was present in the sample in the beginning. The mass of the precipitate is proportional to the amount of analyte present. For example, the more sulfate ions there are in a solution, the heavier or more barium sulfate precipitate will produce. This schematic breaks down a typical precipitation method of gravimetric analysis quite effectively. We will start by measuring the total mass of a particular mixture, followed by dissolving it in water. When it is completely dissolved, we will add a suitable substance to the solution to produce a precipitate. Again, it is important to add the substance in excess in this step to ensure that every possible ion that we want to analyze reacts to form the precipitate. The next step is to pour the solution with the precipitate into a filtration apparatus to separate the precipitate. It is more effective and provides more accurate results than normal filtration using only gravity. In the last step, the isolated precipitate is dried to remove any residual amount of water. Once drying finishes, the precipitate is weighed and its mass is used to quantify the amount of analyte in the original mixture or compound we dissolved in the beginning. Let's reinforce the sequence of steps using a common example, the analysis of a fertilizer. Fertilizers usually contain sulfate and phosphate ions, both of which easily form precipitates with numerous cations. One of these ions is barium ions. Precipitation gravimetric analysis is often used to quantify the amount of sulfate or phosphate ion that's present in a sample of fertilizer. First of all, the fertilizer that we want to analyze is weighed and dissolved in water. Some components of the fertilizer are not soluble in water, so they are filtered before continuing to the next step. The filtrate, which now contains the sulfate or phosphate ions, is treated with excess barium ions. This is usually in the form of barium nitrates or barium chloride. Both solutions are quite soluble. The precipitate formed between barium and sulfate or phosphate ions is then separated using filtration. In the final step, the precipitate is dried and weighed. Before we continue to discuss how the mass of the precipitate is used to calculate the amount of sulfate or phosphate ions, it is important to note a few major assumptions we have made throughout the analysis. Since sulfate and phosphate ions can be both present in a sample of fertilizer, this method only works if the fertilizer contains only one of these ions. Thus, we are assuming only one type of ion in the fertilizer, that is either the sulfate or phosphate, is precipitated by adding barium ions. In addition, since we do not know how much sulfate or phosphate ions there are in the fertilizer, we can only assume that the barium ions that we are adding is in excess. And we ensure that it is in excess by usually adding a large volume of highly concentrated barium solution. When performing filtration, it is important to rinse the precipitate in the filter paper with distilled water. In this step, we are assuming rinsing will help us remove any substances that's not the precipitate or water. While this is ideal, you can imagine it is not very realistic. Let's have a look at how we can use the mass of the precipitate to quantify the amount of sulfate ions in a sample fertilizer. A 0.455 gram mixture or sample of fertilizer contains calcium sulfate. This is the chemical reaction that occurs between barium and sulfate. Using the stoichiometric, the original mass of fertilizer of substances from heating. The second method of performing gravimetric analysis is volatilization. This is when we measure the change in mass of a substance when we remove volatile substances from heating. A good example of this is the analysis of sodium hydrogen carbonate, which is a common ingredient of baking soda. This is done by reacting the sodium hydrogen carbonate with an acid in excess. The reaction between a metal carbonate and acid produces salt, water, and carbon dioxide. As the carbon dioxide is produced, it leaves the solution, causing the total mass of the reaction mixture to decrease. Since we know the mass decrease is due to the gas leaving the open system, This is used to calculate the number of moles of the gas, for example, the carbon dioxide, which is then used to quantify the amount of analyte, for example, the sodium hydrogen carbonate. While performing this type of analysis, we are again assuming the substance we are adding to produce the gas is in excess. This is often tricky to ascertain as we do not know the amount of the analyte in the sample. Furthermore, the second assumption is that the mass change is only due to the gas produced from the reaction. Sometimes there may be more than one gas produced, or the gas may be produced from an unaccounted chemical reaction. Let's look at how the mass change before and after heating can help us determine the amount of sodium hydrogen carbonate. Sodium hydrogen carbonate in the baking soda, molar mass of carbon dioxide. Hydrogen carbonate equals, this gives us 0 carbonate by the mass of the sample to obtain the final value of 49.6%.
Okay. Now the thing is that so just a second. Just a second. So that in the video that you have seen that how does we have to do this means, electrogravity titration, and also the thing is that how to calculate the different types of means value of quantity, how the quantity, what is the procedure, what is the stepwise. First you have to take in the that your that any substance which I have given, that you have to make it diluted properly, then you have to filtration group, or then a little bit more you have to add, that is particular precipitate items. Then when the precipitation will, then the filtration will be there, then crystallization process is there. So that is the procedure and things. Okay, so thing is that now we'll come down to the systematic way. So we'll go that is that the polarization. Okay, you got understand that how, what the polarization is there, and what is the concentration polarization in that video also. So kinetic polarization means how when you that is add that particular precipitant substance to the the substance which that which quantity you have to measure, so that that particular things, the substance, that precipitate substance will pull that substance to the bottom part. That is the precipitation process. So that is the things, the polarization of precipitation, that is mentioned over there. Okay, next thing is that importance of that over voltage. Okay, importance over voltage, that is the standard operation process. You have to understand that. Types of electrogravimetric methods. So constant current electrolysis. So this is that method is that electrogravimetric method, constant current electrolysis. In this procedure, you have to use the constant current, means that supplementary current should be constant. It is given 6 to 2 volt of DC. Okay, 6 to 2 volt of DC, that is you have to use between that particular that current voltage. Okay, of currents. Okay, next thing is that then potential changes during the electrolysis at constant applied potential. So when it will at the constant applied that potential it will use, so what type of changes will be there. So consider consider the that is ions of electromagnetic medium, and thing is that initially the applied potential of the to the cell is about minus 2.5 volt, which lead to a current of about 1.5 ampere, as shown in figure 5. That is it is shown in that figure. Okay, so see, that is this is shown in the figure. Okay, so that means the increase in okay, the thing is that, just a second. Okay, At a reaction process, as the reaction proceeds, IR decrease continuously. Like the decrease is due to the concentration of polarization of the at the anode. So it is decreased to the at the concentration polarization towards the anode, because we learn that how the that ions mobilated towards the different charge, means cathode ion at the equilibrium state. So and to get the equilibrium state, which limits the rate which copper ions are brought to the electron surface of the limiting current of the zone. So that's why the current changes is there, and concentration will be increases towards the cathode sides. Okay. So constant potential electrolysis, in this case, constant potential electrolysis, you have to 2.35 that ampere of current you have to use. So this is the diagram where you see that digital voltmeter is used, digital current matter is the use. So on the basis of that, you have to calculate that one. So that you understand over there. Okay, electrodes, you know that electrodes are that is a metal part which that is release the electrons, or that is release the electron. So electrodes are different types of electrodes. We can use mercury cathode electrode at the mercury. So cathode at the mercury electrode, we can use mercury as in liquid state, but it can wrap with that particular that is any test tube or anything else. Then you can measure it there. Successive deposition of metals, on the basis of that, metal will be means deposited at the respective tubes. Okay, then coulometry. So let's go to the one video. The coulometry is there. So just a second. Just a second.
Good day. I hope you are doing well. By the way, I'm Alexis Rodriguez. And today, I'm gonna discuss about coulometry. Here's the outline of my presentation. To begin, let me start with a short introduction. Coulometry is a group of electrochemical techniques in analytical chemistry. It is named after Charles Augustin de Coulomb, a French military engineer and physicist best known as the eponymous discoverer of what is now called Coulomb's law, the description of the electrostatic force of attraction and repulsion. The SI unit of electric charge, the coulomb, with the symbol C, was named in his honor in 1880. In coulometric methods, the quantity of electrical charge required to convert a sample of an analyte quantitatively to a different oxidation state is measured. Coulometric and gravimetric methods share the common advantage, that is, the proportionality constant between the quantity measured and the analyte mass is calculated from accurately known physical constants, which can eliminate the need for calibration with chemical standards. In contrast to gravimetric methods, coulometric procedures are usually rapid and do not require that the product of the electrochemical reaction be a weighable solid. Now, let's dig deeper into the working principles behind coulometry. First, let us define what is an electric charge. Electrical charge, with the unit C, is the basis of the other electrical quantities, such as current, voltage, and power. The charge on an electron and proton is defined as 1.6022 times 10 to the negative 19 coulombs. A rate of charge flow equal to 1 coulomb per second is the definition of 1 ampere of current. Thus, a coulomb can be considered as that charge carried by a constant current of 1 ampere for 1 second. The charge Q that results from a constant current of I amperes operated for t seconds is expressed in equation 1. For a variable current, small I, the charge is given by this integral in equation 2. Now, let me introduce you to another foremost scientist in history, who contributed greatly to the study of electromagnetism and electrochemistry, Michael Faraday. Faraday discovered the underlying principles behind electromagnetic induction, diamagnetism, and electrolysis. The Faraday, with the symbol F, named in honor of Michael Faraday, is the quantity of charge that corresponds to 1 mole, or 6.022 times 10 to the power of 23 electrons. You may recall that each electron has a charge of 1.6022 times 10 to the power of -19 coulombs. Thus, the Faraday is equal to 96,485 coulombs per mole. Furthermore, Faraday's law relates the number of moles of the analyte A, N sub A, to the charge Q. This is given by equation 3, where N sub A is equal to the number of moles of the analyte. Q is the charge, which could also be derived using equation 1 or 2. N is the number of moles of electrons in the analyte half reaction, and F is the Faraday's constant. Having these definitions, we are now able to calculate the mass of a chemical species that is formed at an electrode by a current of known magnitude. This is the core principle of coulometric methods of analysis. Here is a sample problem for you to apply the working equations involved in coulometry. Feel free to pause this video to practice your skills. To continue, 2 methods have been developed that are based on measuring the quantity of charge. First, there is controlled potential, or potentiostatic coulometry, and then there is also what we call controlled current coulometry, more often called coulometric titrimetry. Potentiostatic methods are performed with the potential of the working electrode being maintained at a constant value relative to a reference electrode throughout the electrolysis. In controlled potential coulometry, the electrolysis current is recorded as a function of time to give a curve similar to curve B in the figure. The analysis is then completed by integrating the current time curve to obtain the charge, and from Faraday's law, the amount of analyte. Coulometric titrations are similar to other titrimetric methods, in that the analyses are based on measuring the combining capacity of the analyte with a standard reagent. In the coulometric procedure, the reagent consists of electrons, and the standard solution is a constant current of known magnitude. Electrons are added to the analyte via the direct current, or to some species that immediately reacts with the analyte, until an endpoint is reached. At that point, the electrolysis is discontinued. The amount of analyte is determined from the magnitude of the current, and the time required to complete the titration. The magnitude of the current in amperes is analogous to the molar concentration of a standard solution, and the time measurement is analogous to the volume measurement in conventional titrimetry. A fundamental requirement for all coulometric methods is 100% current efficiency, that is, each Faraday of electricity must bring about chemical change in the analyte equivalent to 1 mole of electrons. Note that 100% current efficiency can be achieved without direct participation of the analyte in electron transfer at an electrode. Earlier, I have introduced two types of coulometric methods. I will be discussing the instrumentation behind each of those methods. Starting with controlled potential coulometry. The instrumentation for potentiostatic coulometry consists of an electrolysis cell, a potentiostat, and a device for determining the charge consumed by the analyte. These figures illustrate two types of cells that are used for potentiostatic coulometry. The first figure consists of a platinum gauze working electrode, a platinum wire counter electrode, and a saturated calomel reference electrode. The counter electrode is separated from the analyte solution by a salt bridge that usually contains the same electrolyte as the solution being analyzed. The salt bridge is needed to prevent the reaction products formed at the counter electrode from diffusing into the analyte solution and interfering. The second type of cell, shown in the figure, is a mercury pool type. A mercury cathode is particularly useful for separating easily reduced elements, as a preliminary step in an analysis. In addition, however, it has found considerable use for the coulometric determination of several metallic cations that form metals soluble in mercury. In these applications, little or no hydrogen evolution occurs, even at high applied potentials, because of the large overvoltage of hydrogen on mercury. In controlled potential coulometry, a potentiostat with this design is often used. Generally, however, the potentiostat is automated and equipped with a computer or an electronic current integrator that gives the charge in coulombs necessary to complete the reaction, such as shown in this figure. Now, let's go over to controlled current coulometry, or coulometric titration. The equipment required for a coulometric titration includes a source of constant current from 1 to several hundred milliamperes, a titration cell, a switch, a timer, and a device for monitoring current. As shown in the figure, moving the switch to position 1 simultaneously starts the timer and initiates a current in the titration cell. When the switch is moved to position 2, the electrolysis and the timing are discontinued. With the switch in this position, however, current continues to be drawn from the source and passes through a dummy resistor that has about the same electrical resistance as the cell. This arrangement ensures continuous operation of the source, thus aiding in maintaining a constant current. The constant current source for a coulometric titration is an electronic device capable of maintaining a current of 200 milliamperes or more that is constant to a few hundredths percent. Such constant current sources are available from several instrument manufacturers. The electrolysis time can be measured very accurately with a digital timer or a computer-based timing system. This figure shows a typical coulometric titration cell, consisting of a working electrode at which the reagent is produced, and a counter or auxiliary electrode to complete the circuit. The working electrode used to generate reactants in situ is often referred to as the generator electrode. It is usually a platinum rectangle, a coil of wire, or a gauze cylinder with a relatively large surface area to minimize polarization effects. The counter electrode is usually isolated from the reaction medium by a sintered disc or other porous medium to prevent interference by the reaction products from this electrode. Coulometric titrations, like their volumetric counterparts, require a means for determining when the reaction between analyte and reagent is complete. Generally, the endpoint indicators described in volumetric methods are applicable to coulometric titrations as well. For example, in the titration of iron 2+, an oxidation reduction indicator, such as 1,10-phenanthroline, can be used. As an alternative, the endpoint can be determined potentiometrically or amperometrically. These are used in Karl-Fischer titrators. Furthermore, some coulometric titrations utilize a photometric endpoint. In general, coulometry may be used for the quantitative analysis of both inorganic and organic compounds. At this juncture, we will discuss some of the applications of coulometric methods. Controlled potential coulometric methods have been used to determine more than 55 elements in inorganic compounds. Methods have been described for the deposition of more than 24 metals at a mercury cathode. The method have also been used in the nuclear energy field for the relatively interference-free determination of uranium and plutonium. Controlled potential coulometry also offers possibilities for the electrolytic determination and synthesis of organic compounds. For example, trichloroacetic acid and picric acid are quantitatively reduced at a mercury cathode, whose potential is suitably controlled. Coulometric measurements permit the determination of these compounds, with a relative error of a few tenths of a %. Now, we go over to the applications of coulometric titration. As reported in many literatures, coulometric titrations have been developed for all types of volumetric reactions. For example, in neutralization titrations, hydroxide ion can be generated at the surface of a platinum cathode, immersed in a solution containing the analyte acid. Whereas, hydrogen ions generated at the surface of a platinum anode can be used for the coulometric titration of strong, as well as weak bases. Coulometric titrations of acids are much less susceptible to the carbonate error encountered in volumetric methods. Coulometric titrations with EDTA are carried out by reduction of the amine mercury 2+ EDTA chelate at a mercury cathode. Because the mercury chelate is more stable than the corresponding complexes of calcium, zinc, lead, or copper, complexation of these ions occurs only after the ligand has been freed by the electrode process. Several precipitating reagents can be generated coulometrically. The most widely used of these is the silver ion, which is generated at a silver anode. Coulometric titrations have also been developed for many, but not all, redox titrations. This table reveals that a variety of redox reagents can be generated coulometrically. For example, the coulometric generation of bromine forms the basis for a large number of coulometric methods. Here is a short video involving the use of coulometry, specifically coulometric titration, in the determination of water or moisture in liquid samples, using Karl-Fischer titration.
At the rear of the unit are the power switch, the power inlet, the fuses, and the RS-232 and USB connections. At the top and front are the printer, connections for the electrodes, the titration vessel holder, and the front panel. To assemble the glassware, start by placing the titration vessel in the holder. Next, take the electrode leads and attach them to the generator and detector electrodes, and then locate the electrodes on the titration vessel. For more detail on this or any other aspect of the Aquamax KF moisture meter, please refer to the user manual, which is available on the GR Scientific website. The injection septor is fitted into the plastic screw cap connectors and located onto the injection ports of the titration vessel. The drying tube is then filled and fitted. Before adding the chemicals, remove the assembled glassware to avoid spillage on the Aquamax KF moisture meter. Remove the injection port and the drying tube and insert the stirrer bar. Add the full 100 milliliter bottle of reagent using the supplied funnel and reconnect the injection septor. Take the cathode reagent, snap the vial, which has a safety snapper already fitted, and pour the reagent into the inner chamber of the generator electrode. Reconnect the drying tube, relocate the glassware onto the Aquamax KF moisture meter, and connect the electrode leads onto the appropriate sockets. To switch the instrument on, connect to the mains electricity supply using the power pack and mains cord. Press the power on switch at the rear of the unit. The instrument will then start to stir automatically, and the display will show the model, the software code, and what the operator is required to do. All other keypad functions are disabled. Press Start as requested by the display. The Aquamax KF moisture meter begins the precondition process, showing how many micrograms of water have been titrated, the speed of the titration, and the detector signal. After several minutes, and as the process advances and the speed reduces, settle any residual moisture more quickly by turning the unit off and gently swirling the vessel. After preconditioning is complete, the Aquamax KF moisture meter will monitor the background drift and then move into the ready mode once this is stable. Once in ready mode, the keypad is enabled and the instrument can be programmed. The program key displays a scrolling list of program parameters beginning with the sample ID number. This can be up to 8 digits in length. To clear an entry, simply press Clear. To confirm an entry, press Enter. If the sample ID number is the only parameter to be changed, press Clear and the unit will return to the ready mode. It's not necessary to scroll through unwanted parameters. The second parameter is Recall method. Methods can be stored in memory to avoid reprogramming from scratch. The next parameter is Result format. Pressing the decimal point will cycle the format through microgram, ppm, milligrams per kilogram, and percentage. Press Enter to select the required format and then enter again to move to the next parameter. This is calculation mode. The choices here are volume and specific gravity, volume, weight difference, weight and dilution ratio. The Aquamax KF moisture meter will then ask for the values appropriate to the chosen mode. The printer mode parameter gives options for off, for printing every result, or for a full report including time, date, sample number, instrument serial number, and so forth. The statistics print parameter will print statistical data from a series of up to 99 results. The background drift print option may be either on or off. Other parameters allow delay times to be programmed, minimum titration times to be set, and the sensitivity to be changed. The beep can be turned off, set to sound when a key is pressed, to the end of titration, or to both. The user's language can be selected from a list of all common languages. The generator electrode parameter can be set to either with or without frit. This completes the programming, and the method that has just been specified can be saved for future reuse.
Now, let's talk about primary standards. A primary standard is a highly purified compound that serves as a reference material in titrations and in other analytical methods. The accuracy of a method critically depends on the properties of the primary standard. Important requirements for a primary standard are the following: 1. Atmospheric stability. 2. Absence of hydrate water so that the composition of the solid does not change with variations in humidity. 3. Modest cost. 4. Reasonable solubility in the titration medium. 5. Reasonably large molar mass so that the relative error associated with weighing the standard is minimized. 6. High purity. Established methods to confirm purity should be available. Very few compounds meet or even approach these criteria, and only a limited number of primary standard substances are available commercially. One of the most important primary standard in analytical chemistry is potassium hydrogen phthalate or KHP. KHP is widely used both as a acidometric standard for acid and base titration analysis, and as pH standard. The purity of KHP has been determined by precision coulometric titration for about 50 years already. Although a lot of work has been carried out, precision coulometry is still an extremely extensive method, not suitable for high sample throughput. A fundamental apparatus for coulometry is commercially not available. Therefore, individual experimental designs are applied, which are only possible to build up if special know-how, and knowledge of coulometry procedures, and electrochemistry techniques, are available. Handling such complex equipment, and performing precise measurements, are only manageable by highly trained specialists. To overcome these problems, a special experimental design should be developed, to carry out certification analysis of large batches of KHP standards. One proposal is to use a commercially available automatic volumetric titration system, in combination with a reliable software, for the endpoint detection. With this, it should be possible to produce equivalent results, with the same accuracy in comparison to a definite method, handled by a fundamental apparatus, for traceable precision coulometry. This idea was further explored in this study entitled Purity of Potassium Hydrogen Phthalate, Determination with Precision Coulometric, and volumetric titration. A comparison. It was done by Recknagel et al. And published in the journal Analytica Chimica in 2007. The aim of this study was to compare the results of precision coulometric titration with those from precision volumetric titration on the analysis and certification of a specific KHP reference material. The methodology is divided into two parts. First is the purity determination using precision coulometry. Then it is followed by purity analysis using volumetric titration. For the coulometric titration experiment, the determinations were carried out using the system given in Figure 1. This system includes a titration cell with the following specifications. The precision coulometer used was an electrochemical computerized system that consists of a constant current source, an indication unit, a valve unit, and a piston burette. For the measurements, 4 calibrated devices were used. These include an analytical microbalance, a timer, a multimeter, and a resistor. The experimental procedure involves drying of the sample, performing the initial, main, and final titrations, and calculation of purity and measurement uncertainty. For the volumetric titration experiment, titrations were carried out using a modular automatic titration system, consisting of a sample changer and a dispensing unit. For potentiometric endpoint detection, a combined pH glass electrode and silver-silver chloride reference system was used. The experimental procedure involves the preparation of the titrant, calibration of the apparatus, drying of the sample, titration of the sample, and calculation of purity and measurement uncertainty. Now we go to the results. Table 1a shows the results of the 9 coulometric determinations of 3 different bottles of the investigated KHP batch, and the mean, as well as the standard deviation of the mean. Calculation of the uncertainty for the coulometric determination is shown in Table 2. The results of the volumetric determination are given in Table 3. For each of the 35 bottles, the means of 7 single determinations are listed together, with the corresponding absolute and relative standard deviations. There was no hint for any inhomogeneity of the material. Meanwhile, Table 4 shows potential contributions to the combined uncertainty of the results received from volumetric titration. The different results for both methods used for the determination of the mass fraction of KHP are summarized in Table 5. In conclusion, acidometric purity of KHP is statistically not different from 100% purity. Very precise volumetric titration, with regards to bias and repeatability, using optimized procedures shows within uncertainties the same results as measurements with precision coulometry, whereby the volumetric method is calibrated with a certified reference material, and the coulometric determination rely on traceable SI quantities. The purity of KHP is the same, with slightly different uncertainties, while the throughput of the volumetric titration is significantly higher than that of coulometric titration. We have come to the last part to discuss the advantages and disadvantages of coulometry. Coulometric titration is often compared to volumetric titration. Here are several significant advantages of the coulometric method. Coulometric titrations eliminate the problems associated with the preparation, standardization, and storage of standard solutions. This advantage is particularly significant with reagents such as chlorine, bromine, and titanium 3+ ion, which are sufficiently unstable in aqueous solution to seriously limit their value as volumetric reagents. Their use in a coulometric determination is, however, straightforward, because they are consumed as soon as they are generated. Coulometric methods also excel when small amounts of analyte have to be titrated, because tiny quantities of reagent are generated with ease and accuracy through the proper choice of current. With conventional titrations, it is inconvenient and often inaccurate to use very dilute solutions and small volumes. A further advantage of the coulometric procedure is that a single constant current source provides reagents for precipitation, complex formation, neutralization, or oxidation reduction titrations. Among the disadvantages of coulometry in general are the following. 1. Relatively higher cost. 2. Requires highly trained personnel. 3. Long setup time. 4. Limited life of cell. 5. Low sample throughput. Unfortunately, because it is usually not part of a multi-channel analyzer, and highly mechanized coulometers are not available, coulometry can only be used for the measurement of a small number of samples. Well, that's all for today. I hope you have learned something new from this presentation. Thank you for watching.
Okay, these are all about the coulometric and application of that coulometric, and how you work, what is the advantage, disadvantage, how does it work. Everything is explained in that video. So hope that you have to go through your that is syllabus and you understand that things when you connect with the video and all the things. Okay. So now the thing is that another thing is the voltammetry, right? So voltammetry, I'm sharing one video also, voltammetry. Just a second. Just a second.
Good afternoon, sir.
Good afternoon.
Sir, I wanted to ask you that when we will be getting our practical schedule.
Actually, who is asking? Jyoti.
Yes, sir.
Okay, so you are enrolled in which study center?
I have enrolled in Zakir Hussain.
Zakir, so that means in Tamil Nadu or Kerala?
It's Delhi.
Okay, okay. So you just consult with that study center only. Then you can get it, right? So that is it, perhaps it is not fixed for every study center as it is all India class. So I cannot give you the details, exact details, right?
So is it means we will be getting the mails, or we will directly have to go to the
No,
center
no,
for
you
the
just
details?
first see that if it is convenient to you that you can visit to the your nearest study center, it is better for you, right? You will send the mail and you will wait for that one. I don't know that when you will get your mail and all the things. If it is convenient, so visit your study center once, right? So that will be
Okay.
fine for you. Okay,
Okay.
that's all. Anything else?
No, sir. That's all.
Okay, that's fine. Just a second.
not just a nice experiment to do in the lab. It's actually something that does get used in the real world. So one of these examples is one of the products that we have at ZP, and particularly the shape, this kind of duckbill shape that people sort of describe a voltammogram as looking like. If you like the video, please like, be delighted if you also subscribe. And if you have any questions, do put them in the comments below. If you're looking for more mathematics, a nice experiment to do in the lab, it's actually something that does get used in the real world. So one of these examples is one of the products that we have at ZP, which is really for measuring the hotness of chili. But there's also other, for example, medical products. This is a product from a company called Genmark DX, and they definitely use voltammetry. It's actually a ferrocene label in their medical products. So voltammetry, it's not just an academic exercise. It generally gets out there into the market and can make a real sort of world impact. Now, voltammetry does fit into these kind of group of electrochemical analytical techniques. You have amperometry, you have voltammetry, you have potentiometry, and you have an impedance spectroscopy. Now, what's become very powerful in the last few years that all these techniques can now be done, let's say, or powered by electronics no bigger than your thumb or the end of your finger, I should say. So electrochemistry and electroanalytical chemistry has become really powerful, and it's really thanks to essentially modern electronics. So thank you to the IC developers for bringing us these great products. Now, voltammetry, there's lots and lots and lots of voltammetric techniques. So even whenever I say linear sweep voltammetry, LSV, there's subdivisions within this. There's anodic stripping voltammetry, could be considered a form of linear sweep voltammetry. But voltammetry has lots and lots of types. So we have linear sweep voltammetry, cyclic voltammetry, and it's really linear sweep and cyclic voltammetry that I'll cover today. But there's also square wave voltammetry. If you want a video on square wave voltammetry, please drop me a comment down below. Differential pulse voltammetry, the same. If you want to know more about that, please leave a comment. And the same for normal pulse voltammetry. So there are lots of voltammetric techniques, and today we're just going to really focus in on LSV and CV, or cyclic voltammetry.
बाहू इतने सकाळी सकाळी
So cyclic voltammetry, as I say, the first thing we're going to do is really explain this kind of iconic shape. It's one of those kind of symbols that you see throughout the world of electrochemistry. Various manufacturers use it in their logo. You see it on the front of books. So we are really going to describe where this shape of a voltammogram actually comes from. So here we have the voltammetry for ferrocyanide. We're looking at the oxidation and reduction of ferrocyanide. So on one axis here we have the current, often measured in amps or amperes, and we have the potential, often measured in voltage. People get very precious that they sometimes say, oh, that's the voltage axis, and then people say, oh, it's the potential axis. Strictly speaking, it's the potential axis, and the potential is measured in volts. But I don't get particularly precious about it, but some people do. Ferrocyanide is in the solution, and ferrocyanide on the forward scan, and we'll discuss that forward scan in a minute, is getting oxidized to ferricyanide. So Fe2 plus has become Fe3 plus, and then we reverse the direction of the voltage. We go in the we go back again, let's say, and then ferricyanide Fe3 plus, that is reduced to ferrocyanide Fe2 plus. Now the waveform that generates this is called a triangular waveform, and you'll soon sort of see why it's called a triangular waveform. We have a voltage. We start at some voltage. So in this left-hand animation, we start at minus 500 millivolts, and we scan up to plus 500 millivolts. And then from plus 500 millivolts, we scan back to minus 500 millivolts. We have a starting position here, a starting potential here. We scan to here, and then we go back again to the original point. So that's a sort of triangular waveform. So hiding behind every voltammogram, there's a triangular waveform. Linear sweep voltammetry is really similar, except we don't go from one potential to the next potential and back again. We just go from one potential to the next potential, but we don't go back again. Otherwise, they're pretty similar techniques. The only reason I bring this in is at ZP, we are pretty fond of screen printed electrodes. We obviously manufacture our own. We also manufacture potential stats. And the only reason I bring these two images in is because I really want modern electroanalytical chemistry to feel modern. So sometimes you do it, and people have glass vessels and electrodes and cables, and I don't think modern analytical electrochemistry necessarily has to be that way. When we do our science, maybe on our workshops, etc., it's very clean, in terms of, and this is, how modern electrochemistry or modern electroanalytical chemistry really should be presented. I just threw in that E there just to say that ferrocyanide and its oxidation to ferricyanide and the reversal of that is described as an E mechanism. You can have EE mechanisms where you oxidize it once and then you oxidize it twice. That would be called EE. Sometimes you can have electrochemical followed by chemical. That would be called EC. Sometimes you can have electrochemical followed by chemical followed by electrochemical, and that could be called ECE. That's not really what I'm going to dwell on today, but I just want you to know that there are a whole bunch of EC, ECE prime, all sorts of these arrangements, and they really describe the kind of underlying mechanisms. But the oxidation of ferrocyanide to ferricyanide, and that reduction is a simple one. It's just called an E mechanism. So we're going to dive in a little bit deeper now and say, why does this look the way it looks? So I've got a sort of few color coding things going on here. So the first part we're looking at here is we're applying a potential, and we're applying that potential from approximately minus, how can I describe this? From approximately minus 500 millivolts to about minus 150 millivolts. And we've got ferrocyanide in there, but there's nothing happening. And the reason that nothing is happening is because the potential is not sufficient to cause the oxidation of the ferrocyanide to ferricyanide. Now, what happens next then is we hit a region, and I would say this region is approximately minus 150 millivolts to about minus 50 millivolts. And I think that's approximately right. And in this region, we can call it the kinetic region. And what's happening is we are oxidizing the ferrocyanide to ferricyanide. So that is taking place. There's a little equation that describes this. This is the Tafel equation. I'm not going to derive equations today. And the only reason I mentioned the Tafel equation is because obviously if you're trying to learn this subject, there'll be sort of certain equations that you'll be expected to kind of produce maybe in an exam, or, to sort of know about. So I put the Tafel equation in there. This Tafel equation describes this kinetic region. And what it says is my current is proportional to my voltage, but I am not consuming much ferrocyanide, and so I'm only under electron transfer limitations. Later on, you'll see that once you start consuming ferrocyanide, you become what's called under mass transport control, or specifically in a cyclovoltammetry, often diffusion control. Diffusion is just a type of mass transport. So we just went from a region where we had no oxidation of ferrocyanide. Now we're in this kinetic region, just at this foothill, and we describe this as a kind of kinetic region. After that, then we sort of hit a new region. This is kind of they call this the Faradaic sort of region. Faradaic is, there was a Michael Faraday, a very eminent chemist from several centuries back, one of the fathers of modern electrochemistry. So when we have an electrochemical process, people describe it as a Faradaic process or Faradaic current. You will also hear. It's fine. It just means that we're doing some electrochemistry where a chemical is giving up electrons to an electrode, and that would be described as chemical, an electrochemical. That's a Faradaic process. Now, as we go from about minus 50 millivolts up past 0 millivolts, we're increasing the voltage, and all the time the current's going up, and more ferrocyanide is being converted to ferricyanide. But this can't go on forever, because actually there's a point at which we've consumed all the ferrocyanide at the electrode's surface, and we hit this kind of peak. So this peak comes about because we've been transitioning from the foot of the voltammogram, where we were under kinetic control. We started actually consuming the ferrocyanide, and we consumed more and more of that ferrocyanide at the surface, up until a point at which we actually essentially depleted all of the ferrocyanide at the surface, and we reach this peak, and this peak is can be described by the Randall-Sevik equation. The Randall-Sevik equation kind of says that this peak height happens in a simple system to be proportional to the square root of scan rate, and I will discuss that in a little bit. So this, at least first parts, we have a sort of background current because there's not sufficient potential. Then there is sufficient potential to oxidize the ferrocyanide, and we get the kinetic region, and the current starts coming up a little bit. Then we hit this mixed region, because what's happening is we're somewhat under kinetic control, but now the ferrocyanide is being depleted, and actually more needs to diffuse in, and so that's the mix, because we're slightly under kinetic control and slightly under diffusion control. Then we hit this current, because actually this peak rather, and this peak is really indicative that in fact all of the ferrocyanide is now being consumed, and now we hit this kind of transport limited region where the current actually goes down. And the reason this current goes down is because the ferrocyanide is having to diffuse to the electrode from an increasing distance from that electrode. And I have in a couple of minutes, we'll be covering that in a bit more detail. Now there's a moment now where the voltage actually reverses, and then now what's happening is at the electrode surface, all of the ferrocyanide has become ferricyanide, and now we're starting to try and do the reduction of ferricyanide back to ferrocyanide, but we're not providing enough voltage to actually do all of that, but until we hit this kind of kinetic region, at which point now we're in this kinetic region, and actually the ferricyanide is becoming ferrocyanide. We add a bit more potential, and we start actually converting some amount of that ferrocyanide into ferricyanide. So we're sort of reverse of what we were doing earlier on. And again, we hit a moment where we kind of back under this Randall-Sevik, I'm not going to say equation, the Randall-Sevik equation characterizes it, it doesn't drive it, where we don't get any more current, because in fact we've consumed all of the ferricyanide at the electrode, and now we become transport limited again. So this kind of iconic shape is because we have, how would I describe that, at least about 4 different regions. We have the background region, the kinetic region, the mixed region, the peak region, and then that diffusion region. So there's at least 5 sort of regions, and then we reverse it all. So that's why we have such an iconic shape, because of actually this is transitioned from with potential to these different essentially regions, and essentially, yeah, we go from kinetic control to diffusion control. It's probably worth saying that again, you know, if we look at this, that we have that background region, we have that mixed control or mixed region, which is described as the Faradaic current. Again, after that, Michael Faraday, and so we have 2 extremes here. We have that kinetic region, which was described as the Tafel equation, where current is actually just proportional to the potential. And then we have an extreme where actually we hit a peak current. And that reason that peak current comes about is because as we come up this mixed control region, for example, if we start with a solution of 5 millimolar ferricyanide, we have 5 millimolar ferricyanide. And so from the distance from the electrodes, the ferricyanide is all 5 millimolar. But as we come up the mixed region, the potential means that we consume some of that ferrocyanide, and so it drops in concentration a bit, and then we apply a bit more potential, and the concentration of ferrocyanide drops a bit, and then we apply a bit more potential, and the ferrocyanide drops a bit. So what's happening is we're increasing what's called the depletion layer. The ferrocyanide is dropping in concentration at the surface, and more ferrocyanide is having to diffuse in from the bulk, up until the point where the ferrocyanide at the electrode is actually 0, and that's coincidental with that peak there, which, as I say, is described by the Randall-Sevik equation. And the Randall-Sevik equation kind of says that current is proportional to the concentration. It's also proportional to V to the half here, which is the square root of scan rate. And I will describe that again in some more detail in the next slide. So we've been saying, okay, so cyclic voltammetry and linear sweep voltammetry, they're pretty much the same thing. Linear sweep voltammetry, you just go from V1 to V2 In cyclic voltammetry, you go from V1 to V2 and back to V1. But as we change the voltage, the voltammogram is essentially generated at the same time. So we have the scan here, and here we have the resulting voltammogram. And then we have those regions of background, kinetic control, sort of mix control, and we're under sort of transport control here. So we have described that. Now there's a sort of, it's not necessarily an intuitive parameter. It actually says that the faster we go from V1 to V2, the higher the peak current. And it's higher if it's a simple diffusional process like that of ferrocene or ferrocyanide. It's the peak height is proportional to the square root of scan rate, and that's because it's under diffusion control. And this comes from Fick's law. I'm going to describe this not mathematically, but I'm going to describe this with models and animation. So what I'm saying is, the less time it takes to go from V1 to V2, the higher this peak current. And I know that, you know, if you're following textbooks or you're doing lectures on this, this is something that you're taught. But I'm going to try and actually explain it a bit more here. That peak current is really driven by the diffusion gradient near the electrode. So this is the ferricyanide concentration. So in the bulk it's 5 millimolar. This is distance from electrode. And what it says is, when I scan fast, when you scan fast, you go from V1 to V2 really quickly. You hardly have any time to do any electrochemistry, and so you hardly deplete the Fe2 plus and convert it to Fe3 plus. When you go slowly, you actually end up depleting Fe2 plus, and it becomes Fe3 plus. And so the diffusion gradient is shallower the slower you go. And now with this gradient, I'm going to explain to you in a minute, this gradient's actually what drives the peak current. So sharp gradients, i.e. those of fast scan rates, actually give you higher peak currents. Slow scan rates give you shallow gradients of concentration, and they have lower peak currents. So fast and slow. So if you go slowly, you do consume Fe2 plus. You build up what's called the depletion layer. This is the, I say here diffusion layer, but diffusion layer and depletion layer. And actually that gets bigger the longer, or therefore the slower your scan rate. If you do it fast, this depletion layer is very small. And so this gradient here is actually equal, so that gradient is actually equal to the concentration of the bulk, 5 millimolar, the concentration at the surface, which is actually 0. And I'm just going to move myself out of the way slightly and just say that it's equal to the concentration divided by this diffusion layer. So if the diffusion layer is large, therefore you've scanned slowly, this gradient is small. And if the diffusion layer is small, i.e. you scan very fast, then that denominator there makes that number actually quite big. So peak height is a reflection of these gradients, and these gradients get steeper the faster you scan, and that's what's driving this link between peak height and scan rate. And the only reason I bring this up is that it's so kind of iconic or central to, you know, at least when you're being taught electroanalytical chemistry, especially cyclic voltammetry, this is what's driving that. And that's all wrapped up in the Randall-Sevik equation. As I say, it's not something I want to necessarily derive. And the reason I want to derive it is because I think it's better to qualitatively understand this before you, and you can quantitatively understand it. It's just an equation, let's say. It's quite a simple equation once you understand what all the terms are. But knowing the equation doesn't necessarily give you an understanding of what's actually going on. Once you have an understanding of it, you can see then where the terms are coming from in that equation. And as I say, current is proportional to the square root of a scan rate. And I just want to finish with a kind of a last sort of slide on this, which is voltammetry is considered very kind of iconic, and this cyclic voltammetry is considered iconic as well. And I just want to say that the sort of shape that you're looking at It's really just a function of the way you do the experiment. If you did the experiment in a really similar fashion and you're actually rotating, for example, the electrodes, you wouldn't get the cycle voltammetry the way you're expecting. You actually get it. So, for example, if we rotate at 100 RPM, so the same experiment, except I now start to rotate, I'd actually get something that looks a bit like the voltammetry we were looking at earlier on when it was just unstirred under the diffusion control. But the more I stir, then in fact you lose that, essentially that peak, and you hit something that's more like a plateau. So it sort of says to you that the only reason voltammetry looks the way, well, it looks the way it does, one of the main reasons it looks the way it does, is because it's in an unstirred solution. And so as interesting as voltammetry is, and as iconic as that is, it's really just, or that CV is, it's just really a reflection of the way the actual experiment is done. Once you start stirring, then all of this kind of depletion distance or diffusion distance goes away, and you have a new equation at this point, by the way, called the Levitch equation, which says that the current is now proportional to the amount that you stir by. So what I'm going to do now is I'm going to say thank you very much for
Okay, so these are the things that is how the voltammetry works, and the cyclic voltammetry is the important process in the system what you are studying right now. So that cyclic voltammetry, if you go through your syllabus, there is cyclic voltammetry that is similar, that is triangle shape model is there, and how the when you changes that that electrolyte position, then control the current, supplying of a current. So then what will happen? uh, that is how the metal will behave and all the things. These are the that is thing that we have discussed about that thing. Okay, so tomorrow you have class around that 5 p.m, so 5 to 7, so be allowed for that one. Okay, thank you very much.
Thank you, sir. Thank you.